Today's book is the Usborne Introduction to Machine Code for Beginners. Please get your pens and pencils ready and get ready for the most interesting book I've seen, published for kids. The book was written by Lisa Watts, Mike Wharton. It dates back to 1983, obviously beautifully illustrated with lots of little robots, and it's an introduction to machine code or assembly language for the Z80 Zilog processor and the 6502. Z80 used of course in the ZX Spectrum and the ZX81, the 6502 using the BBC micro. It's really good. It goes through everything, how computers actually work, how BASIC works, how memory works, how you look at the CPU, how you translate a program into hex, how you actually load the program into memory, how they actually work, lots of examples, lots of mnemonics, and further reading. It is amazing. Really, I cannot believe that this thing exists, and it is really good. I learned a lot from it. So let's get started. The book describes computers' memory, how memory addresses work, and how the available memory for your microcomputer is divided up into the operating system, BASIC, user RAM, user storage, the screen memory, and so on, how all that works, how hex works, and then goes on into peeking and poking. Peeking lets you look at bytes stored in memory. You just put the address in, it tells you what's there. Poking lets you change the address in memory. So one of the first things it tries to do is say, okay, with these you can change it on the screen. It doesn't work as simply in the Spectrum as it does on the ZX81, which we'll get into later, but I have written a very small program which will peek and poke some data to the screen. Let's have a look. So this is our very simple poking data at the screen. So with the ZX81, each character on the screen is a character in the screen buffer, which is nice and simple. With the Spectrum, it's a lot more complicated. You get each pixel on the screen is a bit in the display, so you get high resolution graphics. Each row of 8 pixels in a character is a byte. So you think, well, they'll all be stored together. No, they're not all stored together. They're stored in rows of 32 bytes across the screen. Okay, then so are they stored the first row, all bytes together? No. You get the first pixel of rows 0 to 7 stored together, then the second pixel, then the third and the fourth. So it essentially loads in 3 different sections. This is why when you see loading screens working, which in the old days, you see them loading in this really odd way. You'd slowly start filling in the lines, and then eventually get the whole screen. After the 3 blocks of data, which is 6K of the screen, you get a block of individual bytes, which represent the attributes. Now here, I've changed all the attributes, but only for the character in the extreme top left-hand corner. It was meant to do it for all of them. It's a bit silly, really. So we're going to fix that now. Here I say I'm poking stuff at the screen. Obviously I've done something wrong. Here we are. The problem is I don't actually change the address. So the idea is I'm going to fill in the data. So what we have is the very first pixel is a hex value of 1, and the second pixel is 2, and 3, and 4, and 5, and 6, and 7, and 8. So each byte is 1 greater than the byte before. So we get this interesting little A shape forming, because that's how the characters work. 1 is 1 bit, 2 is also 1 bit, 3 is 2 bits, 4 is 1 bit, 5 is 2 bits, 6 is 2 bits, 7 is 3 bits, and so on and so forth. After that, we'll load the attributes. The attributes are 3 bits for the ink colour, 3 bits for the paper colour, a bit which says is it bright or is it not bright, and a bit which says is it flashing or not. The colours go from 0 for black, 1 for blue, 2 for red, 3 magenta, 4 is green, 5 is cyan, 6 is yellow, 7 is white, 8 is transparent, and 9 is contrast. I know all these off by heart. So now, hopefully it will work properly. We're finishing loading the screen. About to load the attributes. So we should start off with, so the top line, you have it's black background, then we have blue background, all the different colours. Then we have red background, pink background. And it's all done. So it's all very well having all this machine code gubbins, but you need to get it into memory somehow. With BASIC, you type it in. The microcomputers of the time did not come with machine code assemblers, so you had to get it into memory somehow. What Usborne kindly provided in this book is a machine code loading program. So essentially you load it, it asks you for an address, and then it reads data which is stored as 2-character hex codes, turns them into hex, and then stops. So we're going to give that a try now. It gives some sample data, so let's see what it does. This is the hex loader. All it needs to know is where you want to store the machine code. This is an address in memory. If it works, it just stops. So here we say, okay, that worked. Please tell us what's in memory. That's me trying to run what's in memory. Unfortunately, the data there quite clearly states sample data only. So just there to see, here's the sort of data you might put in if you wanted to run a machine code program. It is not a machine code program. It will never return. It doesn't have a C9 instruction, which is the return instruction. But it's just there as a sample. Before we go further, let's have a quick chat about registers. We're talking about the Z80. The Z80 has more registers than the 6502, so you can store more bytes temporarily in the CPU. So we've got various registers here. A is the accumulator. It's the most important one. It's where most arithmetic is done. It can store 1 byte at a time. F is the flags register, which is set to various flags, such as the carry flag. IX and IY are index registers, which can hold 16 bits. The Sinclair Spectrum manual says do not play with these in machine code, so I steer you clear of those. B, C, D, E, H and L are general purpose registers, which hold 1 byte each, but they can be grouped together in pairs. B, C, D, E, H, L hold 2 bytes each. SP is the stack pointer, and PC is the program counter. So we've now replaced the machine code, the sample code, with real data. We're going to store our machine code not at 32500 but 32504. We're going to load accumulator with the number 2. We're going to add 4 to the accumulator. We're then going to load the accumulator into 32500 and display it on the screen here. It's number 6. What we're now going to do is change it so that rather than having to do the print and the poke and the peek, we actually store the data and it's displayed on the screen. By convention, when you do USR, when you execute machine code by doing USR blah, the data is stored in registers B and C. So at the bottom of the screen you can see 0600, which is store 00 in register B, and then after that you can see 4F, which is store the contents of the accumulator register A into register C. We're now going to do this included sample program in the book, which is called Z80 Screen Flash. We're going to swap 2 blocks on the display with each other, back and forth, back and forth. So essentially we read the memory from register HL, memory register DE, swap them in via register C, keep a counter, promise your uncle. Nice and simple on the ZX81. The Spectrum doesn't hold memory that way. It holds it in streams of pixels. We discussed that earlier. So the code written would work for the very first row of a line of data. That would work fine, except we've got a problem. So as discussed, we can quite easily, with the supplied machine code, swap the first pixel of 2 rows of data. That's all well and good. This is the Spectrum font, which I got from someone's blog called Damien G, link of which will be in the description. Typography and 8-bit system fonts. What isn't immediately apparent is that the Spectrum character set for the alphabet doesn't use the top and bottom rows. You get a bit of space between characters. The only character in the normal typography that does is the copyright symbol. We might be able to see the top of the copyright symbol appearing and disappearing. This is the sample Z80 program provided by Usborne. First thing we do is load a number into the register B. The number is a counter, which is the number of bytes in one block. The sample they suggest is 40 bytes, which would work fine for the ZX81, not so great for the Spectrum. Then we load into the HL register pair address A. The address is the address of the first block, which you supply in hex. However, you need to supply them in low byte order first, low byte then high byte. It does keep in mind this in the book. Then we load into register pair DE, address of the second block, address B. Then we store into register C the contents of the first byte in HL. Then we load the contents of the first bytes in DE into the accumulator. We're doing a swap. Then we load the accumulator into HL, load block C into the accumulator, store the accumulator into DE. We add one to HL and DE, take one from B, put 0 in the accumulator, compare register B with the accumulator. Is it 0 yet? If it's not 0, we jump back F3, which is 2's complement of 13, then return. Rather than the 40 bytes, why not say we've got 2K? Because you only have 1 byte in a register, so we need to do some more code. This is my assembly language program. So we're using the screen buffer of Spectrum, so we're loading into the HL register the address 62384, which in hex is 4000, but you have to load it low byte first, then high byte. Early version of this program got this wrong, and just have it, as we shall see. Next step is loading into DE, the third block on the screen. I later on change this to the second block, but here it's the third block, hex 5000, reverse byte order. Load the accumulator with 0, and then store that 0 at an address. Go round a loop. At the outer loop, we store 128 into register B. So after 128 bytes, we stop. And in the inner loop, thing we repeat over and over again. We load register C with the contents of HL, the contents of DE into register A, and then do a bit of the old swapsy. And at the bottom, we compare with B. Have we got to 0 yet? No. Carry on. After we've got to 0, we've moved 128 bytes. We ain't done yet. We could have used registers to store the counter. We can't. There's not enough registers. We load register A with whatever's in this address we've stored earlier. Compare that with 15. If it is now 15, which we've done it 16 times, we jump to the end. Otherwise, add 1 to it, store it back again, and jump all the way back to load B 128. So this is my first attempt at my program. Here I've possibly stored it in the wrong address. So we try again. Don't store it in random addresses. Store it in 32500. Now it does something, displays it with the screen, goes all pink, and then it crashes. So after lots of work, we're now trying again. We're storing our machine code in 32504. This is because we're using the 32500 to store our counter. So here we use basic program. This is a bit slow to load data onto the screen. We load pretty much A to Z on the top few lines, and then some blank lines beneath. We're now running machine code. You can see here we're pulsing between different characters. What we're actually doing is swapping the first 8 lines with the second 8 lines. The second 8 lines you can't see because they're printed with white ink on white paper. They are the lines beginning with Z. It's a little bit slow, you might think. That's because we put a pause in, because machine code is actually blisteringly fast. So just to prove this, you see here we've got pause 50 on line 250. Let's now change that to pause 5. So we're still going to wait a little bit. 504, off we go. This is basic loading the screen. We could do. I tried to do this in machine code, but it's too hard. Don't do it. It's silly. Press the key to continue, and off we go. And that's with pause 5. Imagine how fast it would go if we just let it run. And this lets you actually get a all in edgewise. So that's why I use machine code. Thank you for watching this little video on machine code for the Z80. The book says, quite right, that unless you're really dedicated, there's no point writing lots and lots of machine code. Some things are done just as well in BASIC. Printing a character on the screen would take a number of instructions in machine code rather than one in BASIC. Loops are easier in BASIC, etc, etc. But for certain things though, like creating the screen effects, machine code is the way to go because it's super fast. Machine code is tricky, it's hard to do, You can get it wrong. If you get it wrong, weird things happen. I had a problem where I was going through my loop an extra time, and with swapping the first and third blocks on the screen, I was then dipping into the attribute area and changing the attributes randomly, which caused odd effects on the screen. When I was typing in the addresses, I got the addresses wrong. I was swapping the first buffer on the screen with some random data. That didn't go so well. If you didn't have your own assembler, you do it by hand. That's prone to error. Calculating displacements is tricky. Going forward isn't too bad. Going backwards, you have to work out the negative number, which is 2's complement. That's tricky. Would you do it today? Of course not. You would write things in assembler if you wanted to. It's actually important for certain dedicated systems and stuff. But seriously, you're going to be using some sort of engine, because why wouldn't you? The book, as always, apart from the graphics, is available on the Usborne website. Go check it out. It's really, really nice. Thank you for watching.